Section 1.1, Inductive and Deductive Reasoning. The natural numbers are also called the counting numbers, and these are the numbers that start with 1, and they're integers, and they keep going, 1, 2, 3, 4, etc. The three dots that we see right here are called an ellipsis, and they mean that 8 is not the last number, but that the numbers continue in the same manner. If a is divisible by b with a remainder of 0, then we say that a is divisible by b. The counting numbers are divisible by 2. The counting numbers that are not divisible by 2 are 1, 3, 5, 7, and we call these the odd counting numbers. Inductive reasoning is the process of reasoning to a general conclusion through observations of specific cases. It's also called induction. Often used by mathematicians and scientists to predict answers to complicated problems. The scientific method is based on inductive reasoning. When we make a prediction based on a specific observations, it is called a hypothesis or a conjecture. Example, biometrics. What reasoning process has led to the conclusion that no two people have the same fingerprints or DNA? This conclusion has resulted in the use of fingerprints and DNA in courts of law as evidence to convict persons of crimes. In millions of tests, no two people have been found to have the same fingerprints or DNA. By induction, then, we believe that fingerprints and DNA prove a unique identification and can therefore be used in a court of law as evidence. Is it possible that sometime in the future two people will be found who do have exactly the same fingerprints or DNA? Interesting question. Okay, let's try a couple examples with mathematics problems. Use inductive reasoning to predict the next line in the pattern. So you want to notice the patterns that we see here. On the left side, we see that the numbers are going 1, 2, 3, 4. The next number stays as 3. And then on the other side of the equal sign, these numbers are increasing by 3. So logically, the next line would be 5 times 3 equals 15. Here's another one. Now let's notice what's happening here. Is the same thing happening as we go for, how do we go from 1 to -2? Do we add a number? We could add what? We could subtract 3, but if we subtract 3 from -2, we don't get 4. Let's try multiplying. What number do we multiply 1 by to get -2? And that would be -2. If we multiply -2 by -2, do we get 4? Yes. If we multiply 4 by -2, do we get 8? Yes. So the next three numbers would be -8 times -2 would give us 16. 16 times -2 would give us -32. And then -32 times -2 would give us 64. Use inductive reasoning to predict the next three numbers in the pattern. To make this problem a little bit easier, it's helpful to have all the numbers written in the same format. So I'm going to go ahead and write that first number as a fraction. Now I can probably see the pattern. The numerators are staying as 1. What's happening in the denominators? Each time I'm adding a 4, right? 1 plus 4 is 5. 5 plus 4 is 9. 9 plus 4 is 13. So the next three numbers in the sequence would be 1 over 17, 1 over 21, and 1 over 25. Use inductive reasoning to predict the next figure in the pattern. So let's take a look. We started with a small circle, then we enclosed it in a square, then we put a larger circle around the square. So logically, the next pattern would include what? A square around that circle, and we see that in figure C. Find the letter that would be entry 87 in this sequence. So again, you want to look at the pattern. And I notice here there's a pattern that repeats in 5s. C followed by 4 Fs. And so what I'm going to do is I'm going to take 87 and divide by 5, and I get 17 repeats with a remainder of 2. So I'm going to go 2 steps into the next repeat. So if I notice that I have 17 repeats, so in the 18th group or the 18th repeat, I'm going to go 2 places. 86 will be a C and 87 will be an F. So the 87th entry is an F. Pick any number, multiply the number by 4, add 2 to the product, divide the sum by 2, subtract 1, repeat this for several different numbers, and make a conjecture about the relationship between the original number and the final number. All right, so let's try a couple numbers. Let's pick 5, multiply by 4, we get 20, add 2 and we get 22, divide by 2, we get 11, subtract 1 and we get 10, And if we go ahead and we do some others, if we start it with a 5, we got a 10. If you try it yourself and start with a 2, you'll get a 4. If you start with a 3, you'll get a 6. A 4 gets an 8, and so forth. So our conjecture would be that when you follow this procedure, the number you end up with will always be twice the original number. In a minute, we're going to prove that using deductive reasoning. A counterexample, in testing a conjecture, if a special case is found that satisfies the conditions of the conjecture but produces a different example, this is called a counterexample. Only one exception is necessary to prove a conjecture false. If a counterexample cannot be found, the conjecture is neither proven nor disproven. So let's try an example. Statement: the sum of any two odd numbers is a number divisible by 3. Let's try some examples. So 3 plus 3 is 6. That's the sum of two odd numbers, and it's divisible by 3. 5 plus 5, two odd numbers, gives me 10. Now remember what divisibility meant. When I divided by the number, I didn't get a remainder. 10 is not divisible by 3, so there's a counterexample. Here's another one. The sum of two squares is an even number, and there's many possible answers here. So 3 squared plus 2 squared, 9 plus 4 is 13. That's not an even number. Here's another example. 1 squared plus 2 squared, 1 plus 4 is 5, not an even number. If the following pattern is continued, how many dots will be in the 100th figure? So let's take a look at what we see here. We started with 3 dots, and then each consecutive figure is adding 2 dots. We have 5 dots here, and 7 dots here, and so forth. So let's get to the pattern here. So to get to the 100th figure, first of all, we need, after the first figure, we need 99 more. And the first figure started with 3 dots, right? And then each additional figure adds 2 dots. So we can actually write an equation. The total dots is the dot in the first figure, 3, plus we need 99 more figures that each add 2 dots. Go ahead and simplify that. There'll be 201 dots in the 100th figure. Deductive reasoning is the second type of reasoning process, and this is where we go to a specific conclusion from a general statement. So again, we're going to show this in our pick a number example. Prove using deductive reasoning that the procedure we showed earlier will always result in twice the original number selected. And what we're going to do this is we're going to start with a general number rather than a specific number. So we're going to pick a number and we're going to call it n. And then we're going to multiply it by 4. We're going to add 2. We're going to divide by 2. So when I take 4n plus 2 and divide by 2, 2 goes into 4n 2n times, 2 goes into 2 one time, and then I'm going to subtract 1, and look what I end up with, 2n, which is exactly what I said when I picked specific numbers. So we've now proven that the answer actually is 2n.